Okay, so let's take a look at C. And I've had to write it out by hand because what was on the slide was slightly different from what's in the notes. But thankfully, what's in the notes is a little more manageable, although this is going to be tricky. Okay, but we can handle it. All right, so the first thing I'm going to do is try to identify a feasible delta x. Okay. And I say feasible because we might have to play with some things and tweak it a little bit, but we're going to go with that. All right, so looking at this, I can see that everything is being multiplied by this 8 over n. So that may be a good value for our delta x. In the previous examples, delta x always came out to be something nice and convenient like 1 over n. But of course, it doesn't have to be that way. We already knew that. So let's see what happens if we identify delta x as 8 over n. The thing about this, though, is that if this is what we say delta x is, then we've got to be consistent with that. So um, we'll keep that as our definition unless we have to change it. Now we're going to take a look then at the definition of delta x along with what may appear to be our x sub k, right? We can see that this thing is the natural log of something. And so this is the something that we're talking about. Um, it looks a little different, but let's go with the fact that A could be 1. All right, so let's just say A is equal to 1. And of course, we know that delta x is B minus A over N. So we're saying B minus A is equal to 8. If A is 1, then B has to be 9. All right. So let's say that all of this is right. We're still trying to figure it out. All right. So I've got delta X, I've got A, I've got B. So the next thing I need to look at is X sub K. All right. We know X sub K should look like A plus delta X times K. All right. And so using the values that we've already um, determined, then we see that this would be 1 plus 8 over n times k. All right. The problem with that is that that's not what's plugged into the natural log function. Okay. In our natural log function, we've got 1 plus 16k over n, right? And what that means is that this is not simply the natural log of x. Okay, it's the natural log of something else, and we need to try to kind of figure out what that something else is. Whatever we've done to x, the result of it is 1 plus 16k over n, right? And by the result of it, I'm talking about what we have right here, okay? This is how we're going to be able to express our x sub k's. We're plugging it into some function, um, into a natural log function, and not just a simple natural log function. We're going to be multiplying or adding or something. So we got to kind of figure out how that's going to happen. All right, so when I look at these two things that we have highlighted in yellow, one of the differences, the main difference is that for one of them, we've got 8 over nk, and when whatever's done to that, it needs to come out to be 16k over n. So basically, what I'm recognizing is that we need to double this 8 over nk. All right, so let's say we do that. All right. How could that work? If I said, okay, I'm going to look at 2 times x sub k, all right, then that would come out to be 2 plus 16 over n k. All right, that almost works, except now this thing is too big. I don't need 2, I need just 1. So far, let me back up. What we've done is basically 2 times our x. That's what we got. So if I subtract 1, all right, then we have this expression, 2 times x sub k minus 1, and that would actually give us, if we simplify this, 1 plus 16k over n. So what we're taking the natural log of is 2x minus 1. All right, so now we're ready to write our integral that represents this. We're going to look at the integral from 1 to 9 because we said a was 1 and b is 9. And we can see it's the natural log of 2x minus 1 dx. And that would be an equivalent expression. We can check that on the calculator to make sure that it is equivalent. And let's just go ahead and do that just to make sure. All right, so we'll do the integral first. So that's going to be math and number 9. Okay, we're integrating from 1 to 9. And we're looking at the natural log of 2x minus 1 dx. Okay, we want to make sure we got all of our parentheses. I believe I need to add a close parenthesis right here. Okay, yes. All right, there we are. All right, so that comes up to be 16.08. If we can, we'll convert this to a fraction. And that's not necessarily convenient to write, but it is exact. All right, so we started out with this summation. Okay, so let's see what that looks like. All right, we've got 8 over n, or we'll say 8 divided by x. All right, and we're going to use our summation. So math, I believe that one was choice 0. We're going to sum for k equals 1 to n, or x. And we're looking at the sum of the natural log of 1 plus 16k over n, or 16x divided by n, or I'm sorry, 16k divided by x. Okay, and I believe that's correct. All right, we've already multiplied by 8 over x. All right, so let's see what that'll give us. So if we do alpha trace to get our y1, and let's just go ahead and push this up to 1,000, we get 16.09. All right, so we can see that as the number of rectangles approaches infinity, the value of the Riemann sum is approaching the same thing that we found when we used integration.